Welcome all of you for the last lecture probably in this series on properties of a nucleus. So before we started discussing the properties of a nucleus, we also looked at atom, the Bohr model, and before that we also studied photoelectric effect, wave particle duality and so on. So in a sense, as I told you, in all probability we will be concluding this set of lectures today. I cannot claim that I have covered all the topics in your syllabus, but whatever is a matter of information or whatever you can easily pick up, I have left it out, but I will certainly indicate what is it that I have left out as I go along. In the last lecture, what we did was to look at great detail on the process of fusion. So we were able to understand the processes that are going in the stars, especially our own star, the sun, as to how such an enormous energy is related. And although we did not even attempt to describe qualitatively the theory underlying a fusion process, it is way beyond your 12th standard. In fact, it is way beyond even in your undergraduate studies. Just by making use of mass energy equivalence and energy conservation, we were able to work out what we will call as energetics and argue how energy is produced and how it is able to sustain itself. That is only one part of the story, because there is the other part of the story where the nucleus can actually decay. In the first case that we have studied in about 2 or 3 lectures is the coming of lighter nuclei together to produce heavier nuclei, and in that process there is a mass defect. They lose some of their mass, so produce a daughter which has a higher value of A, atomic number or atomic weight, higher value of Z, but then it has lesser mass than the masses of the incoming particles and energy is liberated. That is what we found. And I described some cycles for you, carbon cycle, etc., etc. And I told you that eventually everything should end up with iron, because iron is the most stable of the nuclei. It has the maximum binding energy per nucleon. Therefore, iron cannot go to anything by itself unless you are going to violently perturb that, act on it. You can always break iron. For example, if you send very highly energetic proton or a neutron or another nucleus, but by itself it is a very stable nucleus. That is the statement that we made. Today what I want to do is to look at the other side of iron nucleus, which will give rise to fission, and also the unstable isotopes of various nuclei. It could be carbon, it could be boron, whatever, is that okay? As to how they undergo decay. There are essentially 3 decay mechanisms, the so-called alpha, beta and gamma. Alpha refers to helium nuclei, beta refers to either electron or a positron, and gamma of course is electromagnetic radiation, what we call as the photon. So before I start discussing that, I should actually round off my discussion something by telling you something about the age of the stars. Remember, we told that as the mass of the star keeps on increasing, its lifetime actually keeps on decreasing, because there is more and more material and therefore there is more and more fusion that is taking place. So what we are interested in is actually showing you as to how the lifetime of a star depends on its mass. So that is the first thing that I am going to look at, and this is a brief recall of the carbon cycle that I told you, as to how you start with hydrogen, you produce helium and then go via lithium and then produce a carbon, which is a fairly stable isotope because it sits on the top among its neighbors in the binding energy per nucleon. What we want to do is to show you the effect of this on the masses of the stars. So this is the picture that I have been repeatedly showing you. So if you look at it, so I am going to focus on carbon. You see, carbon's binding energy per nucleon is larger than all its neighbors, and of course oxygen is even larger, so that is the next cycle. But at the topmost in this whole spectrum of binding energy per nucleon is iron. This is something that you have to remember. That means if you look at nucleic molybdenum or tungsten or whatever or uranium, they would all like to decay and come back to iron, whereas these fellows would like to keep on fusing and come back to iron, provided sufficient conditions like temperature or whatever are there for fusion processes, and this is a figure or a graph which you should hold very close to your heart. It is an extraordinarily informative graph. So, here is the lifetime which I have picked up from literature. So, now you see our standard for the mass of the sun is of course sun. So, when I say it is 1, it actually refers to 1 solar mass. So, our sun would typically live for about 10 billion years, and if you imagine that the solar system and the star, the sun, they were all formed roughly at the same time, okay, because of collision between two stars or whatever depending on the astrophysical model, then our earth is about a few billion years old, maybe 2 or 2.5 billion years old. So, we need not really worry about what the fate of the sun will be for the next 8 billion years. It is an enormous time. Now, if I jack up the mass by let us say a factor of 1.5, you see correspondingly the lifetime comes down to 3 billion. It goes down by a factor of 3. It goes up by 3, factor of 3, it becomes 370 million. So, it is falling very fast in a super exponential manner, probably certainly in an exponential manner, okay, with a very large value of the decay constant, whatever that constant is, and by the time the mass acquires something, mass of a star is something like 60 times the mass of the sun, it would live only for a few million years, 3 million years. Dinosaurs, I think, were there a few million years ago. So, this is an extraordinary thing, and this can be estimated simply by the the amount of nuclei that are there, the rate at which they are burning, etc., simple kinetics. So, I would encourage all of you to see that. If you come back to this graph, of course, I should also mention what would happen if there is a super light star, let us say of 0.1, that would live for thousands and thousands of billions of years. So, stay light, live longer is not only the dictum given to us humans. We should not become too obese at any age. It seems to be also true of the stars. Okay. So, I want to, whatever I told you, I would like to repeat, because it certainly bears repetition, it is a very important thing. And this graph clearly shows you, on the left hand side it is the fusion that generates energy, on the right hand side it is the fission that generates energy. Okay. Iron is standing at the borderline, and you have all these things, copper, molybdenum, strontium, tin, xenon, etc. So, whatever was shown in the previous graph is reiterated by showing the line explicitly. Okay. This sort of concludes whatever I had to round off from my previous lectures. What we are now going to do is to look at new phenomena, namely fission, radioactivity, gamma decay. Gamma decay, of course, is also a part of radioactivity, but then I have written it separately because it is a slightly different phenomenon compared to the others. I will tell you why in a minute, and that is the reason why I have written it separately. These are the things that we are going to look at. So, let us start with nuclear fission, and remember I have shown you the graph. The condition for a nucleus to break into smaller nuclei is z squared by a must be greater than 47. That is a very important thing. If you look at the lighter nuclei, the most stable ones are those for which z is equal to roughly a. If z is equal to roughly equal to a, equal number of protons and equal number of neutrons will be there, z is equal to a by 2. But as we keep on going to heavier and heavier nuclei, the nucleus becomes bigger and bigger. We know that r equal to r naught a to the power of 1/3. That is what we are writing. So, the nucleus becomes bigger and bigger. When the nucleus becomes bigger and bigger, the strong interaction, the nuclear force between distant nucleons, either protons or neutrons or protons and neutrons, become weaker, because I told you nuclear force is a very short range force. But on the other hand, the repulsion between the protons and the neutrons keeps on increasing. That becomes dominant because of the electromagnetic force. Therefore, what you do is to actually tend to increase the number of neutrons to compensate, and that is the reason why this is an important parameter, z squared by a must be greater than 47. So, here is a canonical example which I am showing. The famous decay of the uranium, 235 uranium, it spontaneously undergoes a decay into 140 xenon plus 92 strontium, and it emits 3 neutrons in that process. So, you can add them up and you can see what you are going to get, and the energy liberated is about 173 MeV. So, one might say we have an unlimited source of energy, because all that we have to do is to collect some heavy nuclei, put them together, and then they will start producing energy by decay. I do not have to do anything at all, just as I am receiving the radiation or energy from the sun. But the catch is that the probability per decay is 10 to the power of minus 11 per second. So, on an average, if you have 10 to the power of 11 nuclei, maybe one of them would decay. So, it does not do much for us. Is that okay? And that is the reason why we are not interested in spontaneous fission, but we are interested in what is called as an induced fission. I am not going to get much into it. So, this is something that you can remember. So, there are certain thumb rules in that we have to follow, and I am sure you people would have worked it out any number of times in your class. So, what are we going to write? There is a parent nucleus which is going to x1 plus x2, maybe some alpha particles. Actually, that also I can write it as a nucleus, but let me write it explicitly. Maybe some betas and maybe some gammas. So, this is what I am going to write. So, this is some kind of a generic process. It is split into 2 nuclei. I am showing helium separately because we are interested in alpha decay. In that process, it may emit some beta and it may emit some gamma. So, I will put an N1 beta and then N2 gamma. Let us say it emitted N1 beta particles and N2 gamma. Now, this beta itself can come in 2 species, such we are going to see. So, it can either be the electron and it can be the positron. Is that okay? So, this will be, let us say, R1 and this will be R2. R1 plus R2 is equal to N1. That is what we are writing, the total number. So, what is the statement that we want to make? In this process, there are 2 things that we have to check. That is, this product, initial quantity A should be heavier than the sum of the masses of all these fellows. The mass of A should be greater than the sum of the masses of all the outcoming particles, including the energy of the gamma particles, number 1. Number 2, you should conserve total charge. Remember, my protons carry a positive charge, my positrons or the so called beta plus carry a positive charge, and electron carries a negative charge. So, in all these processes, the basic account keeping involves conservation of energy, mass defect, and conservation of total charge. So, in your exam you will be asked any number of chains and you will be asked, tell me how many protons decayed, how came out, how many neutrons came out. All that to do is to balance this. Is that okay? But before I do that, I should know a little bit more about beta decay, and that is what I am going to come to in this. So, what are we going to do when we look at beta decay? So, basically, as I told you, my beta minus is a notation for electron, beta plus is the notation for the positron. This is a hangover from earlier days of nuclear radioactivity, when people knew nothing about the electrons or the basic particles. The electron was being just discovered. So, all of them were called as radiations because they produce some kind of a scintillation or whatever on the detector. And then what people did was to actually put magnetic fields and actually ascertain that they were carrying a charge. Positron was of course discovered much later, but anyway, so these are the things that people have seen. Is that okay? So, the notation is beta minus is electron, beta plus is positron, alpha is nothing but the nucleus, the so called helium nucleus, and gamma is nothing but your photon. That is what we have, and let us see what is happening. The first thing that we have to look at is the gamma decay, because that is the simplest. In the case of gamma decay, actually a nucleus is not undergoing any decay. We all the time speak of radioactive decay, radioactive decay. Actually, gamma is an example where there is no radioactive decay. It is a perfect analog of the atomic de-excitation. So, let me remind you what we studied in the case of the atoms. So, in the case of atoms, for example, hydrogen. So, you have the ground state and you have the first excited state, second excited state, so on and so forth. And if I remember correctly, this gap is 10.4 electron volts. Well, this must be n equal to 2, this is equal to 1, this is n equal to 3. So, basically 13.6 divided by 4. So, that gives me 4 3s are 12, 3.4, that is what I have. So, 13.6 to 10. So, it is not 10.4, but 10.2 electron volts. So, what do you do in the case of hydrogen atom? For example, you can heat the hydrogen atom to a very high temperature. What would be the temperature be? Of the order of, let us say, 10 electron volts. 1 electron volt is something like 10 to the power of 4 Kelvin. So, let us say 10 to the power of 5 Kelvin is what you are going to do. Is that okay? 0.1 million, 1 lakh Kelvin, is that okay? At that temperature, there will be enough energy to excite the hydrogen atom into the first excited state. And then what will it do? It will emit, it will get de-excited and come to the ground state. The atom is not doing, it was in an excited state, and then it simply comes down by what is called as spontaneous emission, and it produces a gamma. So, it produces a gamma in that particular process, and that is what you study. Of course, you can study the inverse process. I can send radiation of the order of 10.2 electron volts, and then you will see that there will be an absorption, and it will go and sit there, and after a while it will come down, whatever is given by the dynamics of electromagnetic interactions, is that okay, that lifetime, and then what you see is a sharp line with 10 to the power of whatever 10.2 electron volts coming, and this is a de-excitation process. In a similar manner, if I were to go to the nucleus, so far we have discussed only what? The size of the nucleus, the mass of the nucleus, etc., right? R equal to R naught a to the power of 1/3, how the volume depends on A, so on and so forth. Actually, it turns out just as atoms have excited states, molecules have excited states, okay? In a similar manner, nuclei also have excited states. This was known when people started studying nuclear reactions. So, in those reactions, for example, when if you excite it, it has to come down to the original state. The nucleus has not changed its identity or its nature at all, except that it was sitting in an upper level, it comes down. As to what the energies of the excited states are, that is a different matter altogether. But when such a thing happens, when it comes down, it emits gamma rays, just as my atom emits gamma rays. That is what is happening. So, I have given you two examples here. Here is 10 beryllium in its first excited state. It comes to the ground state by emitting a photon. Is that okay? In a similar manner, here is a heavier nucleus, 13756 barium. Is that okay? Everyone has heard of barium. That again comes down from its first excited state to the ground state. Now, suppose somebody showed you the information on the photon emitted by an atom and the photon emitted by a nucleus. How would you distinguish whether it came from there or not? The answer is always in the length scale, the time scale, and the energy scale. Atomic phenomena are governed by energies of the orders of electron volt, whereas nuclear phenomena are always governed by the orders of a million electron volt. That is what you found in fusion, right? Mass defect is of the order of MeV. In a similar manner, if strong interactions are strong and have a short range of about a Fermi, 10 to the power of minus 15 meters, from that we can infer that the corresponding energy scale is about a million electron volt. So, these will be typically of the orders of million electron volts. They are very, very high energetic gamma particles. Is that okay? They have, and that is what we see. And the most important thing is that you see neither the atomic weight nor the atomic number changes. Of course, the energy changes because you had supplied some internal energy to the system. That is something that your people have studied in your thermodynamics course. So, whatever energy you supplied, that went as an internal energy of the atom, and then it got de-excited and it comes. So, this is about the gamma decay. The next one is what we call as alpha decay, and here is a nice picture which is telling you how 240, I think it is plutonium, is going to uranium and an alpha particle. So, when we are looking at alpha decay and a gamma decay, we have to make a fundamental distinction, and that is why I am going to see, showing you this specially. So, you can see that initial value of A What is A? The nucleon number. The total number of protons and neutrons was 240 and the final one is 236. That means it has lost 4 nucleons. That means the total number of protons and the total number of neutrons lost is equal to 4. But now if I look at the charge, initially the total number of protons was 94 in the parent nucleus. In the daughter nucleus it is 92, that means it has lost 2 protons. That means the whatever has come out because of the decay, the particle is carrying 4 nucleons and a charge of 2. That means it is helium nucleus 4H2 2He. That is what we have. So let me write down explicitly because that will be an example for us throughout, because I am not going to work these problems anymore. So what we have is 240 plutonium 94 going to 236 uranium 92 plus 4 helium 2. So what is the balancing that we have to do? 236 plus 4 is 240, 92 plus 2 is 94. But it does not end here. What should you do? You should look at the mass of plutonium, you should look at the mass of uranium and you should look at the mass of helium. पहले से शुरू करना है क्या? So what we shall do is to see that my 240 plutonium 94 has decayed into 236 uranium 92 and 4 helium 2. So what is it that I was telling you? 236 plus 4 is 240, 92 plus 2 is 94. Therefore, we have taken care of the total number of protons and the neutrons. But more important is that I have to look at the mass of the parent nucleus and the 2 daughter nuclei. Is that okay? We call this as a particle, although that is also a nuclei. So if I look at MPU and I look at MU and I look at MHE, I am looking at this. What am I saying? This has a rest energy associated given by MPU C squared. This has a C squared and this has a C squared and this is greater than this plus this. So this decay was possible because the total energy contained in my original nucleus MPU C squared is greater than the rest energy is contained. So what is happening to the rest? It will go as the kinetic energy. Remember, my alpha particle is produced with a certain momentum, so it starts coming with a momentum. If my nucleus is decaying at rest, there is a recoil momentum, so that goes as the kinetic energy of the 2 particles. And in any case, there is a jargon which you people should know, and that is M parent minus MD1 plus MD2. So I am writing alpha decay, right? So let me call it as helium, M helium. This into C squared is called the Q factor. Basically, it is the mass defect multiplied by the C squared, and this is responsible for decay. So this is the same old mantra everywhere. That is what we are going to say. Energy conservation, momentum conservation, charge conservation. These are the 3 accountants whom we should always respect and whom we can never violate. So that is an important statement that you have to note, and that is what we are going to do. Now comes the beta decay process, and the point that I want to make for you is that there is a fundamental difference between beta decay and alpha decay. So maybe I made a comment in the previous slide. So if you look at the top, there is a statement which I made, there is called a compound nucleus. So in this process, you can actually pretend as if my plutonium is a compound nucleus. It is a compound, just as elements forms, atoms forms compounds, molecules. Is that right? That is what we are going to form. In a similar manner, we can, to some extent, in fact to a large extent, assume that my plutonium itself is a compound of what? Uranium and alpha particle, and it just turns out it is not a very stable compound. It decays, and when it is going to decay, what is going to happen? One of the constituents of the compound comes out, and then that is what we are going to see. But then when I am starting look at beta decay, my beta decay is coming. So this is the universal feature. Let me first discuss the universal feature and then go to the distinction. You have AXZ. So what do you mean by that? A is my atomic number, my Z is my atomic weight, Z is my atomic number. Let us call A as the nucleon number. So when it decays, my electron has negligible mass. Remember, my proton is 2000 times heavier than an electron, so I don't worry about that small quantity here. In any case, the total number of protons and nucleons will remain the same, but the total number of protons will increase because I produced an electron, I produced an extra charge, and the total charge should be conserved. Therefore, what should happen? Initially, if there were Z protons, there must be Z plus 1 protons. That means one of the neutrons actually emitted an electron and it became a proton. That is something that we are going to look at. And the other piece of information that you should be familiar with that is that although initially Becquerel and Curie and all these people could not see this, it was actually initially proposed, predicted by Pauli based on conservation of angular momentum, so on and so forth. It is accompanied by a particle called antineutrino, which we denote by nu bar. At this point, you don't have to worry too much about what the properties of the antineutrino are, what its nature is, except that for all practical purposes, it is something like photon. That is, it travels with the speed of light. It has no rest mass. Is that okay? And it is also something like an electron, because just as electron carries spin half, we discussed that intrinsic spin, my antineutrino also carries a spin half. Now the other process is the beta plus decay. Remember, I told you beta plus is the positron. What happens in this particular case? If you have emitted a positron, that means the total charge in the protons plus neutrons must go down. That means one of my protons becomes a neutron. The total number remains the same, but the number of protons decreases, and in that process it emits a neutrino. Neutrino and antineutrino, they are both massless, they don't have charge, they don't have spin, but still they are distinct particles. They are distinct particles. And how do you distinguish them? It is like, in your chemistry course, you study about left-handed molecules and the right-handed molecules. Some molecules go like a right-handed spiral, some molecules go like a left-handed spiral. There is a corresponding properties between neutrino and antineutrino. You don't have to worry about that. So they are distinct particles because of their chirality or the handedness nature. Is that okay? So this is the universal feature. That is something that we have to know. What then is the difference between alpha decay and a beta decay? So let us spend some time on that. That is very, very important. I have already hinted at that for you. In the case of alpha decay, the 4 particles, 2 neutrons plus 2 protons were inside the nucleus. So this is like an escape. Just as a person can escape from a prison or a confined area, the person was already there. It is just that you were able to break open the barrier and come out. What is happening is that the particles were already there and they simply break open the barrier and they come out because, and for that reason we say there is no production as such. In the sense that production is a production of something which was not there. But when it comes to beta decay, I told you that when I write A, X, Z, there are Z protons and A minus Z neutrons. There are no beta minus or beta plus. That is the most important thing. So what happens is that the particles undergo a transmutation. That is the most important word. Is that okay? They undergo a transmutation. they undergo a change in the property. So, what happens? A neutron actually becomes a proton. In fact, that is going to come in the next example, and then it produces an electron, and then it produces a antineutrino. That is the most important thing. In a similar manner, my proton, I will put a star here, I will let you know why, can become a neutron plus a positron or your beta particle plus a neutrino. So, when a proton in a nucleus becomes a neutron, we say that there is a beta plus decay. When a neutron becomes a proton, we say there is a beta minus decay. You see, the particles have changed. Initially, the particle did not have any charge at all, but now it has acquired a charge. It is a strongly interacting particle. Initially, my proton had a charge, but after the decay it lost its charge, but it continues to interact strongly, and in that process it produced a particle which was not existing. It gave birth to two particles actually. In this case it produced an electron and an antineutrino. Here it produced a positron and a neutrino. That is what it did. And therefore, although in the initial days of nuclear radioactivity, when Becquerel and the Curie couple discovered, they did not make any distinction. They called all of them decays, alpha, beta, gamma, etc. There are fundamental distinctions. Gamma is because of the de-excitation, alpha is because of the escape of two protons and two neutrons, and beta is because of the production of new particles. That is something that we have to remember. I have put a star on a proton and I will tell you why, and for that what we shall do is to go to the next slide. Okay, I think I will come back to this slide after looking at this particular example. So, the first example that you see here is my neutron going to proton plus electron plus antineutrino. Remember, there is always one person who is all the time looking behind us and seeing to it that we don't cheat. And what is the cheating that we should not do? We shall not violate conservation of energy, conservation of momentum, and conservation of charge. Now, if you therefore look at it, you see my neutron is becoming a proton, an electron and an antineutrino. First thing is to conserve charge. My neutron is a neutral particle. I am sorry about that. My neutron is a neutral particle. It produced a positively charged particle, namely the proton. It produced a negatively charged particle, electron. The magnitude of the two are the same. Therefore, the net charge is 0. And antineutrino, of course, does not carry any charge. So, it is perfectly fine. Now, if you go to the other example, this is what we are interested in. 14 carbon is an isotope of carbon. 12 carbon is a stable isotope. 14 carbon is not a stable isotope. So, what 14 carbon does is to look at its surrounding nuclei with the same A. Is that okay? And 14 nitrogen actually turns out to have a lesser mass. So, what does it do? It says, I will go and sit in that state with lesser energy, and in that process it produces an electron. So, what is happening? One of the neutrons in the 14 carbon becomes a proton, so it goes to 14 nitrogen, it emits an electron and it is a nu bar, and that is also perfectly consistent, no problem at all. But the most interesting case is 10 carbon. 10 carbon is again another isotope. What have you done? You still have 6 protons, but you have only 4 neutrons. That is what you have done. If you look at this, it is producing 10 boron, which is very good, and it is, okay, thank you. So, it is producing a neutrino and a positron. That means what are we saying? One of the protons converted into a neutron. So, let me make a few statements on that. So, basically we are saying that the fundamental process is proton going to neutron plus Na plus nu. Now, we are in for trouble. If you go back and look at the masses, my mass of the proton is less than mass of the neutron. That means we are not conserving energy, and of course, that must be correct because hydrogen is stable. Hydrogen atoms have been there for billions of years, they are not going to decay into anything. Proton is a stable particle, whereas neutron is not stable. You all know that it has a half-life about 13 minutes or so. So, if that be the case, if I come back to this picture, how is it that in this carbon decay, my proton is able to go to a positron? And the answer to that is in what I am going to write, and that is what I have to explain. I said P star goes to neutron plus E plus nu. Although a free proton cannot decay into a neutron, a proton inside a nucleus can decay, because there are other surrounding particles which can give the missing energy. Therefore, what we have to do is to worry about the conservation of total energy, is that okay, and not of individual constituents. That is something that you have to remember. Therefore, what should we do when I come back and look at this? I should look at the mass of 10 carbon, I should look at the mass of 10 boron, I should look at nu, I should look at E plus. Then what will it give me? It will immediately give me consistency with conservation of energy, conservation of momentum, conservation of charge, and this process is therefore allowed. So, in that sense, we have looked at three particular processes: the gamma decay, the alpha decay, and of course the beta decay, and we have found out what the distinctions between them are. All of them of course are coming from a nucleus. In that sense they are common, but they are also different from each other. But then it is also true that they share one more common feature, and that is in the law that governs their decay. That is the famous law of radioactivity, which I am going to come to. So, you see, to club them all under radioactivity is not incorrect, it is perfectly fine, provided we understand the distinctions between these three processes. That is something that we have to remember. Of course, if you give me a nucleus, it is not going to tell me I will only going to decay this way, that way or anything. So, here is an example, probably it is there in your textbook, of what we call as a chain reaction. What is a chain? A goes to B, B goes to C, C goes to D, etc., etc. So, it will trigger a chain of reactions. That is what we have. So, here my parent is thorium 23290. What will it do? It will first emit an alpha particle and produces 22488 radium. Is that okay? That is what it is going to produce. Now, this radium is also unstable because of the, I told you how the mass factors are. So, that will produce actinium, which is 22889 by a beta decay. You see, therefore, they will look at which is the best place for them to go. That is what they are going to do. Actinium goes to thorium again. Don't confuse this thorium with this thorium. They are two different isotopes. Here it was 232, here it was 228. That means there is an extra 4 neutrons in this. Then it produces E minus, and thorium again goes to another isotope of radium and 4H2E. So, in this process, when I start with a heavy nucleus, it will start looking all around its surroundings, and it will keep on emitting particle going to the nearest neighbor, which is favorable because of the proximity, because of the energy difference, because of charge conservation, because of the rate at which processes go. The rate at which gamma emission takes place is not the rate at which beta emission takes place, is not the rate at which alpha particle takes place. Is that okay? They are all governed by different dynamics. So, I am not telling you anything about the time scale here. So, if you look at this, this is what is an example of a chain reaction. So, this chain reaction is illustrated very nicely. Is that okay? It is color coded. So, even if you can't see what it is, you don't have to worry. Is that okay? Basically, you start with uranium 238. So, this is what I am showing. It keeps on coming. So, whenever there is this pink color, you call it as an alpha particle. So, whenever there is the blue, for example, that means it has emitted a beta. Is that okay? And of course, this lead 206 is a stable nucleus, and after that there is no further decay. It is going to sit there. Is that okay? When I say beta, it may be either beta plus or beta minus, again depending on the energetics. Is that okay? There is a nuclear stability line. You have to go either to the right or left, depending on whichever is more favorable. So, this is a very nice process that you have. And of course, we have to give the credit to the radioactive.eu.com, who have carefully made this figure and compiled it. This is a very, very nice example. This is another example of the same kind, which is more involved, and I wrote the first few fellows for you, so you don't have to worry about that. So, let us stop there. So, in other words, we have fairly well understood the qualitative features of what is happening with what? The radioactive processes, alpha decay, beta decay and gamma decay. Now we have to go to the quantitative features. As I told you, in the quantitative features, what is happening is that all of them are governed by a universal law. However, in stating this universal law, I should be very, very cautious and careful. I should also try to be precise, because otherwise it conveys a completely different impression, which happens many times when you read the book. So, what are the things that we have to know? The things that we have to know is, to start with this slide. Actually, I am going to look at the third line. In radioactive decay, what matters is probability. That is the most important thing, and maybe I should spend 1 or 2 minutes on that. All of your classical mechanics, is that okay, Newton's laws, planetary motion, etc., were all completely governed by deterministic evolution. That is, there was no question of probability. When you people solve, you say, my particle is in a cross electric and magnetic field, my charged particle. It has an initial position and it has an initial momentum. Where will it be after a time t? There is no question of probability, you will predict it precisely. In a similar manner, a planet is in an orbit. At this particular point, it is at this particular position. Where will it be? You know that. That is how we are able to predict eclipses, we are able to build machines, we are able to do a whole lot of things with our technology, because there is no question of probability. Of course, you have probability in statistical mechanics, but there, or thermodynamics, but there the probability is because we do not have the initial information. The problem is not with the dynamics, but with the lack of information. But here, when I come to law of radioactivity, this probability is fundamental. You give me all the information, but you can never predict what the nucleus will do. So, if there is a nucleus, you cannot ask how long will a nucleus live. You can only ask what is the probability that after a certain time it has survived or it has decayed. That is the probability that we have to ask. We have to write an equation for the probability. So, that means when I speak of probability, it is necessarily statistical in nature. How do I verify laws of probability? One sample is not going to be doing that. You have to perform a large number of repeatable experiments, keep on repeating them under identical conditions. If you perform them, then you will be able to extract probability. That means you need law of large numbers. So, for example, you cannot ask a question, there was one neutron and after about 13.5 minutes what happened? We do not know what happens. It can either be there, it cannot be there. So, when we speak of half-life or mean life or whatever, you should understand it is statistical in nature. But unfortunately, we frame questions like there were 10,000 nuclei, radioactive nuclei at a certain time t, given its lambda, how many nuclei are left after a certain time, let us say t equal to 10 seconds. Strictly speaking, it is not a very, very good way to form. When we say 10,000 nuclei, we are assuming that is a big enough number for us to realize probabilities, but there are certainly bound to be some deviations. That is something that we have to remember. This feature should not be forgotten. So, once we do that, it is remarkable that people, by looking at all these radioactive sources, in fact, Marie Curie succumbed to her experiments. At those days, people did not know that this hard radiation can actually cause cancer. Is that okay? It did cause for her and she died because of that. That obeys what is called as the law of radioactivity, which I am going to come in a minute, and I have written that. So, if you give me the summary is here, decay rate depends on the population at that instant. So, what am I saying? Suppose at a given time t, there are n of t number of parents, let us call it as a nuclei. Then the decay rate depends on how many of them are there. If there are very few of them, then very few of them decay. If there are very large number of them, very large number of them decay. That means underlying is probability. That is what we are saying. Is that okay? And this probability will get multiplied by the number of particles or number of nuclei that are there. Therefore, number of decays is proportional to the number of participating nuclei. There is nothing great about that. Therefore, dn by dt is given by minus lambda n of t. That is the statement that we are making. So, this rate depends on lambda n of t. That is what we have. Lambda, of course, is a positive constant. If lambda is very, very large, lot of them decay. If lambda is very, very small, very few of them decay. If lambda equal to 0, of course, none of them decays. That is what we have. So, if you look at R, which is minus dN by dt, that is called activity. Activity is nothing but the rate at which something decays. Is that okay? Therefore, I have put a minus sign here. So, R is lambda into n of t. So, what is the equation that I am going to write? Let me write it for you. My dN by dt minus lambda n, I should put a time here and I should put a time here. That is what I am going to write. And R by definition is lambda n into t. This is my activity. So, if there is a decay process, you see, activity decreases with time. This activity, of course, depends on time. So, how are we going to write that? R of T1 is lambda n of T1 and n of T1 is n naught e to the power of, okay, we will come to that in a minute. R of T1 is equal to lambda n of T1. R of T2 is lambda n of T2. T2 greater than T1 is what I am writing. Therefore, RT2 over RT1 is NT2 over NT1 is less than 1. Because as time passes, number of nuclei which have not decayed become smaller and smaller. There were many more at time t equal to 1 than T2. So, with time my activity keep on decreasing. If you look at the definition of my activity, what did I write? I wrote R of t is equal to lambda n of t. This is my number which is dimensionless. And this is minus dN by dt. Therefore, lambda is, dimension of lambda is 1 over t. That is the time scale. Its inverse is the time scale for the decay of a particle. So, my dimension of RT activity is 1 over t. Now, when you speak of 1 over t, which is something like the same dimension as the frequency, you have to provide a units, and there are two units. One is SI, in which it becomes second inverse, and another is Curie, CI. People should be familiar with that. So, let me write it again here. So, my lambda has two dimension units. In SI, which is second inverse, it is called Becquerel. Becquerel is the person who discovered the radioactive phenomenon of radioactivity, and another is Ci. It is denoted by Ci, which is Curie. Becquerel is not a practical unit. Like for example, if you want to study atomic physics, you are not going to use meter or centimeter. It is not a practical unit. Or if I want to give the length of a table, I am not going to give it to you in nanometers. It is not a practical unit. In a similar manner, if you want to study the activity for radioactive phenomena, Curie is a practical unit. So, I have written it down here. That is equal to 3.7 into 10 to the power of 10 becquerel. You get the point, right? I am not going to, so 3 into 10 to the power of 10 per second. That is what you are going to write. So, you wait for that long, and normally all of activity is given. For example, if you go to a hospital where radiation is done, or a nuclear reactor, etc., etc., Curie is the unit that is being used, and that is the first thing about the decay. I have not written down one slide, which is of course, which can of course be worked out at this particular point, and that is the solution. And all of you are completely familiar that decay law equation. So, if I write dNt by dt is equal to minus lambda n of t. I can integrate it dn by n minus lambda dt. So, I am going to integrate it from 0 to t, 0 to t. So, what will I get? I will get log n of t by n of 0 is minus lambda t. That is what I am going to get. So, what is my solution? My solution is simply given by n of t is equal to n naught e to the power of minus lambda t. All of you are thoroughly familiar with this, and this is what is called as an exponential decay. This is what is called as an exponential decay. It is not a linear decay. In a linear decay, the rate or the velocity would be independent of time. Particle is moving with a uniform velocity. The particle is having a uniform deceleration that does not depend on time, whereas here it depends, it is an exponential decay. It falls off very, very rapidly. So, once you realize that, there are two important physical concepts, and that is contained in this particular slide. Okay? And those two concepts are half life and mean life. So, half life is given by log 2 by lambda, mean life is given by 1 by lambda. Let me explain that to you and leave you. So, what do we have? Half life So, what does half life mean? N of t is equal to n naught e to the power of minus lambda t. At t equal to 0, n equal to n naught. At t equal to t half, that is the notation, right? T half, n equal to n naught by 2. So, roughly half of them will survive at some particular time, and this is called half life. And this is a very important concept, because this half life is how we characterize the decay of most of the things, and obviously there is only one time scale lambda, therefore, you should depend on that. So, let us calculate that. So, what would that quantity be? So, we are interested in n of t half is equal to n naught e to the power of minus lambda t half is equal to n naught by 2. That is what we are writing. Therefore, e to the power of minus lambda t half is equal to half. That is what we have, and I will leave it as an exercise. Therefore, my t half is nothing but log 2 by lambda. One minor point to which you should pay attention is that this is in the natural logarithm, and we are not writing the common logarithm. Anyway, its value is known, 0.693. This is what you have. Now, there is something called a mean time, which is an average time, and that is a pretension. Why is it a pretension? Because we say that suppose the rate were the same, but now the question comes, how can the rate be the same? The rate is keep on changing. The rate depends on the total number. So, now what I ask is, in order to discuss the mean life, when would all the particles decay if the rate were the same at t equal to 0? That is a question that we ask. The answer to that is very, very easy to find out. In that case, we would have written n of t is equal to n naught minus lambda n naught into t. And this is not the real n naught. I will put an n bar. Is that okay? and n bar equal to 0 when t equal to 1 over lambda, identically equal to tau. That is what we write. Therefore, tau is my mean time and log 2 by lambda, so they differ by a factor of log 2 is my half life. Obviously, mean lifetime is not a very important concept, but certainly the half life is an extraordinarily important concept, and this figure tells you what it is. So, we have plotted n as a function of time. T half is the time at which the number of nuclei becomes half its original value, whereas tau is an extrapolated value. At this point I will calculate the tangent to the curve and extrapolate, I will get tau. This is 1 over lambda, this is t half, is that okay? 2 over lambda, and this picture should illustrate for you whatever is happening. There are two more things that I should tell you, I do not have to write. In general, there are going to be sequential processes. I told you the chain. So, let us look at the sequential processes. A1 decays to A2 by a constant lambda 1, at a rate lambda 1 given by the constant lambda 1. A2 goes to A3 given by lambda 2 until it hits this table An. How will we write the equation? First we will write d1 by dt is minus lambda 1 n1t. But when I do dn2 by dt, of course, that depends on how fast it decays. Therefore, lambda 1 n1t minus lambda 2 n2t, so on and so forth. So, you know how to write a chain of equations and you know how to solve them. You do not have to get into that. In a similar manner, if there are multiple decays, suppose the same particle can go to multiple decays, then you add them up. So, that will give you the relative decays, and in this sense, this essentially concludes whatever I had to tell you about the radioactive processes or the fission and the fusion. Controlled fission I have not told you, but you can read them up. So, in some sense we have covered all of modern physics through this set of lectures, and I hope that you will be benefiting from them. Okay, have a great day.